Hello everyone, welcome to the 12th session, which is an interaction session on the course and control systems. My name is Soumya and I am a PMRF student at IIT Gandhinagar. And since we have entered into the last week of the course, so we would basically deal with questions related to compensators. Once we are done with compensators, then we'll look for other MATLAB problems as well. But before that, we'll go with this. So, yeah, we'll have a brief revision. We'll start the questions. And the questions are pretty simple. It's not even a full compensator design. It's like chunks of all the parts that goes into making of a compensator to meet the desired performance specifications. So all of them are presented here in the form of questions. Okay, so we'll go through them. So uh, so I hope you have already attended the lecture on compensators. So you might have read that there are lead compensators, lag compensators, and lead lag compensators as well. So all of these are really important and they are same as controllers. So it's like PI and PD controller. But let's see what they bring to the table when they are used as compensators. Where are the zeros placed? Where are the poles placed? And how they have an impact on our system. So let's start with lead compensator. So what we really do with lead compensator or why we actually require it, because it adds sufficient phase lead to reduce any excessive phase lag associated with the system. So we already read like gain margin and phase margin, everything, right? So if you have some phase lag and you might be really close to minus 180 degrees, you might be reaching the verge of instability. So the amount of lead you have that helps in being away from the instability situation. So that is what this lead compensation compensator does. It actually gives you an excessive phase lead to deal with the phase lag. Yeah, it can amplify the high frequency noise. We'll see this shortly that why this happens. The most important thing is that a transfer function of this compensator is of this form. Kc alpha into Ts plus 1 upon alpha Ts plus 1. So this is something that you're supposed to remember when you express it in the form of a pole and zero format. You can really see that there is a 0 at minus 1 by t and there is a pole at minus 1 by alpha t, right? Alpha is supposed to be in between 0 and 1, t is greater than 0, and kc is definitely a gain and it is going to be positive. So what we really see that the lead compensator introduces an open loop 0 at minus 1 by t and an open loop pole at minus 1 by alpha t, right? So it can be expressed in j omega format and you can see that these are the corner frequencies. You are very well aware of the corner frequencies, right? Okay. So Um, after this, yeah, all of these were already taught in the lecture. Yeah, this is really important that we'll be dealing with. So phi m is the maximum phase lead provided by the lead compensator at a frequency omega m. So what is that phi m? Okay. So that phi m is really given by sine phi m is this whole expression. So we had a very similar question in the last interaction session where we actually uh, found out what is the maximum phase lead that can be provided. This is the same kind of situation where you try to take sine of this upon this because the tangent line that is perpendicular to the radius of the circle would definitely give us the maximum phi m. No other angles would give here. So tan phi m is equal to this quantity, right? From here on solving this for angles, you can also find that omega m is equal to 1 by under root alpha into t. So omega n is basically the geometric mean of both the corner frequencies, 1 by t and 1 upon alpha t, right? Now, so yeah, what is important here is that why do we even go for lead compensators? You arrive at a situation where you really don't know you should go for lead compensator or lag compensator. You have to select one, right? And if you to select one, you have to see that what is the requirement that my system has. So we observe from the log magnitude plot. So this is a log magnitude plot if you plot for any lead compensator. The magnitude of the open loop transfer function at low frequencies. Low frequency region means this region, right? This region. Um, yeah, the magnitude of the open loop transfer function at low frequency is decreased. We really have a low frequency over here. Potentially lead to increase in steady state error. Now, how does this impact the steady state error? I mean, everyone should have a clarification that how the magnitude at low frequencies leads to really increase in steady state error. So you know very well that, let's say if I talk about ESS, for some type of system it is either 1 by Kp plus 1 or 1 upon Kv or 1 upon K, right? So if it is of all these types, so if the magnitude is really low here, it is decreased here, the gain is really low here, that means that all of these quantities will have low magnitude, and if they have low magnitude, then the overall steady state error becomes larger, right? So that means that this low gain creates a problem with steady state error. Okay, next, if we increase Kc to address 1, then the high frequency components would also be amplified, right? You'll be amplifying this thing also. And if you amplify this thing, what is going to happen? You're going to take in more high frequency components. That means the system would be more prone to noise. All right. So that is also a problem. Okay. So we read that the frequency between zero and cutoff frequency is called bandwidth of the system, right? So if the bandwidth is higher, bandwidth being higher means omega c is much higher. If omega c is much higher, that means that we have a faster transient response because the bandwidth has increased, but it leads to an increase in cost. Okay, so we want a system with higher bandwidth, but that leads to an increased cost, and we definitely want to have a faster transient response as well. So there is some kind of trade-off between them. So if you increase the gain crossover frequency, the bandwidth increases with compensation. But we needed to introduce a high open loop gain to ensure that lower frequency components were not attenuated. That leads to an increase in cost, right? Okay. Once you read about the lead compensator, you can see there is something called lag compensator, and it comes into picture to attenuate high frequency components of the system response. Basically, we don't want high frequency components to be present. That leads to increase in noise. In this case, it is a very similar transfer function where only the thing which is different here is beta. Beta is greater than 1, t is greater than 0, and kc is greater than 0. Open loop pole is at this position, open loop 0 is at this position. There are two corner frequencies. I hope that is already clear to you. Now, okay, yeah, it acts as a low pass filter. What is low pass filter? Low pass filter is a filter which allows the lower frequencies to pass through and really attenuates the high frequency components. So in the similar way, the lead compensator was a high pass filter, right? This is a low pass filter. Low frequency okay, here the low frequency gain is high as compared to the lead compensator. So if this low frequency gain is high, the steady state error is low, right? Okay, gain crossover frequency for the compensation system leads to reduced bandwidth. All right. Now, we'll also read lag lead compensator, and yeah, lead compensator improves the stability margins but may decrease the steady state error accuracy, whereas lag compensator attenuates the higher frequency components because the bandwidth is decreased and the system is not prone to noise anymore. The compensator can be represented in the following ways, in which we basically have a combination of both lead and lag compensator. Okay. Here, instead of alpha, so we already saw in the lead compensator that in the denominator we had S plus 1 upon alpha T1. But that alpha used to lie in between 0 and 1. let's say we want to eliminate the factor of having everything in be 0 and 1 and making everything to be greater than 1. So this gamma greater than 1 comes into picture. All right. So this is a very general transfer function of lag lead compensator. And if you make any one of them, you can eliminate any one of them. Okay. Frequently we choose gamma is equal to beta. Okay. Let's move to the questions. So, based on all the things that we read until now, we have some questions, conceptual as well as numerical. We'll see. So, which of the following is true about a lead compensator? Uh, okay. It attenuates high frequency signals and worsens the transient response. Does it attenuate high frequency signals? No, because it acts as a high pass filter. If it is a high pass filter, it will always allow this to pass. And it was no, it does not worsen the transient response because it always helps in improving the transient response by improving the bandwidth of the system. So this is definitely not an answer to this question. Let's move to the second option. It improves the transient response and amplifies high frequency signals. Okay. So definitely in our case, we already saw that it improves the transient response and amplifies high frequency signals because it acts as a high pass filter. So it takes, it is more prone to now noise. So this is the correct option for the first question. Okay. Okay. Moving to on to the second question. A lead compensator introduces an open loop pole at -2 and sorry, open loop 0 at -2 and an open loop pole at -20. Then what are the corner frequencies of the compensator sinusoidal transfer function? Let's see this. So the general form in which we had the compensator transfer function, it was given by right. This was the transfer function, controller transfer function. Minus 1 by t is equal to -2 as per the question, and minus 1 by alpha t is -20. Okay. So what are the corner frequencies? Corner frequencies are given by 1 by t and 1 upon alpha t, which is 1 by, sorry, which is 2 and 20. Right? So your corner frequencies are 2 and 20. Okay. In the same problem, in the same question, the maximum phase lead provided by the lead compensator is, what is the maximum phase lead? We already saw now. Tan inverse of 1 minus alpha upon 2 root alpha. Okay. We already know from the last question that 1 upon alpha is, was it 10? Let me check. Yeah, from here you can find out what is on 1 upon alpha. So 1 upon alpha t is equal to 20. So 1 upon alpha into 1 upon t. 1 upon t is what? 2 is 20. That gives you 1 upon alpha to be 10. So from this is the relation which you can use here. 1 upon alpha is equal to 10, right? From here we can find alpha is equal to 0.1. Okay. Then phi m is equal to tan inverse of 1 minus 0.1 upon 2 into under root of 0.1. You can simplify this equation and let me know the answer. I guess no one is solving right now, so I'll proceed, but you can solve it later on. So the answer that you'll get here is something approximately equal to 54.9 degrees. You just have to put in the values and take the tan inverse. It's nothing else. It's 54.9 degrees. All right. Then, okay, the frequency at which maximum phase lead would be provided, which means we want to find out omega m corresponding to phi m. What is omega m? We already saw that it is the geometric mean of both the corner frequencies, 1 pi t into 1 upon alpha t, or under root, which is basically 2 into 20, right? This was the value that we had found out. So under root of 40, which is equal to 6.32. All right, this makes sense. Okay, these are very simple questions. These are just the extracts from how would you design a compensator. Uh, Compensator can be designed using root locus method also, but we are not doing that right now. But it's a whole process, and this is just sub part of a single question. So there are many problems that everyone should practice, which would have a complete process related to compensator design. All right. Now, in the same problem, it is desired that the low frequency magnitude value of the compensator sinusoidal transfer function is 0 dB. So we want the low frequency magnitude value to be 0 dB. Then what is the value of the parameter Kc? All right. So what was our compensator transfer function? I'll copy it for you. Okay. Okay, so this was your transfer function, right? We want to find everything at low frequency. Now, if you take the magnitude of this transfer function, what would happen? Let's replace it by j omega. So, this becomes C of j omega, Kc alpha, Tj omega plus 1 upon alpha Tj omega plus 1, right? Once you do this, and then if you take out try to find out the magnitude, what is going to happen? This omega is small because we wanted to do everything at low frequency. Since this omega is small, it is going to eliminate both the terms. This term is 0, this term is going to be 0, you'll only get 1. So ultimately, the magnitude that we have is just Kc alpha at low frequency. Okay. So the question that is being asked is, it is desired that a low frequency magnitude in dB of the compensator sinusoidal transfer function be 0 dB. So 0 dB is 20 log 10 of the magnitude, which is Kc alpha, right? Now, for this to be 0, Kc alpha should be equal to 1, right? Because log of 1 is equal to 0. So from here, Kc is equal to 1 upon alpha. Alpha was 0.1. So this is 10. Okay. So the value of the parameter Kc is 10 here. I hope everything is clear until now. Okay. Let's move forward. So the next set of questions that we have, the 5 questions, will be based on this transfer function. Please note it down with you. 1 upon s into s plus 2. It is desired that a lead compensator is used to design a unity negative feedback closed loop system with this plant. Okay. So again, we want to have a lead compensator that needs to provide a maximum phase lead of 45 degree. Then what is the value of alpha? So it is going to use the same formula that we used last time also. It's phi m is tan inverse of 1 minus alpha upon 2 root alpha. Okay. Since we want to have phi m to be equal to 45 degrees, tan of 45 degrees is 1, right? So you'll have 1 here when you take tan on the other side as well. And here you'll have 1 minus alpha upon 2 root alpha. So 2 root alpha, sorry, 1 minus alpha is equal to 2 root alpha. Square both the sides. It's 2 root alpha square. So it is 1 plus alpha square minus 2 alpha is equal to 4 alpha. From here, you can find out 1 is equal to 0. From here, you can derive what is the value of alpha. There are two values of alpha that you're going to get. Definitely, we need to check which of these alphas are really valid. So once you find out the roots of this quadratic equation, you'll get them equal to be 0.172 or 5.83. When we read about this lead compensator, we actually saw that the value of alpha should be in between 0 and 1. So definitely we will discard this value and take this value with us. So this is the value of alpha for maximum phase lead of 45 degrees. Okay. Okay. Now, if this maximum phase lead angle should be provided at a frequency of 8 radian per second, then what is the value of t? Okay. So we already know omega m is 1 by under root alpha into t. So from here we can write t is equal to 1 by omega m into root alpha. Omega m as given in the question is 8 and root alpha was 0.172, right? You can find this to be equal to one of the options. Please solve them. Since I have already solved, I have the answers ready with me. But anyway, you should like go through this complete exercise. So this is going to be equal to 0.3. So you have an option here, 0.3. Okay. Now, it is desired that the static velocity error constant be 5 per second. Kv should be equal to 5 per second. Then what is the value of Kc? Now, how is Kv defined? There is an expression that we had arrived at when we were reading about steady state error. Okay. So Kv is equal to 5 per second, right? From here, if Kv for lead compensator is given by limit s tends to 0 s gs hs. This is what we had derived when we did everything like srs upon 1 plus gshs when we wanted to find out what is the steady state error. So there was something in which we manipulated the closed loop transfer function so that we get something in the which has some expression related to es. So that bias upon US was broken, or YS upon RS was broken into some other parts, which gave us a transfer function corresponding to ES upon RS. And from there, we tried to find out what is the steady state error. So it's the same thing. Then we can write limit s tends to 0, s into what is your transfer function? Kc alpha into Ts plus 1 upon alpha Ts plus 1 into what is the complete forward transfer function? You'll have the planned transfer function as well, right? S into s plus 2. We want this to be equal to 5. Let's cancel the terms out here and put s is equal to 0. So from here we'll only get Kc alpha upon 2 because the other terms would cancel out, right? Kc alpha upon 2. Kc is equal to 10 upon alpha. 10 upon 0.172 as from the previous question. So it is equal to approximately 58.1. So this is the value of Kc that you get when you want to have a static velocity error constant to be equal to 5 per second. Okay. All such questions are important. Okay. So this lead compensator, the one that we are discussing right now, 1 upon s into s plus 2, introduces corresponding to this transfer function. Thus, this lead compensator introduces an open loop 0 at around what? So let's find what is the open loop 0. So your 0 is equal to minus 1 by t. And what is the value of t that you had got? It was 0.3. We discussed this in question number 7, that this is equal to 0.3, right? From here we are picking the same value, minus 1 upon 0.3, and it is minus 3.33. Okay, so the lead compensator introduces an open loop 0 at around this point. Okay, where does it introduce an open loop pole? It introduces an open loop pole at minus 1 by alpha t. And if, from the last question, we found out the value of minus 1 by t. We can directly substitute it here upon alpha. So this is your, and you'll get it equal to this option. All right. So this is the way in which we are supposed to find out what is the open loop pole, what is the open loop 0. It is very clear from the transfer function of the compensator that it is just 1 upon t, minus 1 upon t and minus 1 upon alpha t. The corner frequencies are same, just you have to remove the minus sign. So that is a simple way to remember in case you are forgetting it. Okay. Now, in question number 11, consider the transfer function of the lead compensator whose parameters have been determined in problem 6 to 10, last questions. The low frequency magnitude in dB of the compensator's frequency response transfer function would be around what? This is a very simple question. You just have to do everything at low frequency as we did in the last question as well, where we just had Kc alpha. Okay, so your low frequency magnitude is 20 log of Kc alpha dB. 20 log of Kc alpha is 10 here in our case, which gives us 20 dB. So your low frequency magnitude is 20 dB. All right. Okay. Which one of the following statements is false about a lag compensator? So we already saw. Okay, let's go option wise. We want to find out which of the following statements is false about lag compensator. It attenuates high frequency components. So what we had seen, it is a low pass filter. So this is definitely correct because it really attenuates. It increases the low frequency gain. This is also correct because your steady state error decreases. You really have low pass filter characteristic. It reduces the steady state error, the same option. It increases the system bandwidth. It does not increase the system bandwidth. Okay, since it is a low pass filter, your cutoff frequency is going to lie some way before. It's not going to go into high frequency region. So it increases the system bandwidth is the correct answer, and it is false about a lag compensator. Okay, now a lag compensator introduces an open loop 0 at -20 and an open loop pole at -5. Then what are the corner frequencies of compensator's transfer function? Before this, no, it's fine. Okay. So what is your open loop 0? It is -20. That means minus 1 by t is equal to -20. That means 1 by t is equal to 20. What is your open loop pole? It is -5. So minus 1 by beta t, where is t, is equal to -5. That means 1 upon beta t is equal to 5. So your corner frequencies are 1 upon t and 1 upon beta t, which is 20 and 5. Okay. So this is your answer. Okay. The next question, consider a lag lead compensator where T2 is greater than T1. This is important because it will help you in determining what are the position of the poles and zeros. Which one of the following statements is true about the two open loop zeros and the two open loop poles introduced by the compensator? Before going with this question, I'll bring your attention back to this transfer function. So the transfer function of lead lag compensator is given in this way. So you see this part comes from lead compensator. This part comes from lag compensator. I hope this is very evident from the things that we read before this. It is just that you have gamma greater than 1 here. You had alpha less than 1 there, but we brought the alpha to the numerator and said it is gamma. So your gamma is greater than 1 here. Beta was already greater than 1. T1, T2 were already greater than 1. Kc is definitely greater than 1, not greater than 0. T1, T2 and Kc, all of them are greater than 0. Okay, so this is really a combination of lead and lag compensator. Okay, now what we want to make some statement on the position of the zeros and poles. So let's see what happens. So what are the four things that we need to take into account? 1 upon -1 upon T1, right? Okay, this and minus gamma upon T1. This comes from lead compensator. Another two things are uh, -1 upon T2 and -1 upon beta T2. We want to place them on the real axis. Where would they lie? All of them are real, right? None of them are imaginary. So let's place them. So given that all the terms are greater than 0 and gamma and beta both of them, just a second, I'll admit. Okay. And gamma and beta both are greater than 1. So we need to place them at 4 positions. So let's start with so since beta is greater than 1 and T2 is already greater than 1, so it is going to be the least one. Right? Least one in the sense it is going to be more closer to the imaginary axis. because it is going to have a the highest magnitude, and when you take the minus sign, it is going to be closer to the imaginary axis. The second term would be minus 1 by T2, because T2 is greater than T1. Since T2 is greater than T1, 1 by T2 is less than 1 by T2 is less than 1 by T1, and minus 1 by T2 is greater than minus 1 by T1. So here you'll have minus 1 by T1, and the last part would be gamma upon T1, because gamma is also greater than 1, and it is also present in our denominator, so magnitude is going to be higher, but with minus sign it is going to be the lowest quantity. So based on this whole arrangement, what would be true? These both are, sorry, these both are zeros, and both of these are poles. So what would happen? Open loop poles do not lie between open loop 0. This is true, right? This is the first option, is only your answer. I hope this makes sense. Okay, moving on to the last question. Considering the magnitude plot of the Bode diagram of typical lag lead compensator, one can conclude that. So we had a sample example in the lecture that was already delivered to you by professor. So in that, this sample example was taken, and here you could easily see that how both lead and lag compensator are helping in attenuation. Lag compensator is actually helping in attenuation at higher frequencies, and lead compensator is really helping you to increase the bandwidth of the system. So this has the merit of both the compensators, and you can really see that there is something in this zone, some mid frequency zone, where the signals are being attenuated. Okay, so the components corresponding to this frequency are being attenuated, and what is this? Intermediate frequency band is attenuated. Okay, so I think you should draw the Bode plot corresponding to this transfer function and really see if you are getting this. This was already covered in the lecture as a part of homework, it was given to you. So please plot this, and when you plot, you'll find that why lead lag compensator helps us achieve both the objectives. Okay, so this was already related to the compensators. And with this we reach the end of course. So as the part of course summary, we really started with very basic dynamic systems, where we classified the systems as LTI, causal, SISO, dynamic, in all sorts. Then we also characterized the dynamic systems. We went to ODEs, learned about Laplace transform. Then we had transfer function, from which we derived what are the poles and zeros, what is free response, what is forced response.
Ma'am,
Just a second. Hold on.
hello. Mhm.
Yeah, please.
In previous question, I have one doubt, ma'am.
Yeah,
How to know the intermediate frequency, ma'am?
you can know from the plot. So if you draw the Bode plot, you will definitely if you have, see, if you have this type of transfer function, mm, okay, if you have this type of transfer function, you proceed with drawing of the Bode plot, where you find out the corner frequencies, you plot it according to, so what were the basic building blocks of Bode plot? We already saw it was S. 1 upon S, Ts plus 1, 1 upon Ts plus 1, and there could be one more in which we have a second order system. So if you have something of this sort, all of these are the basic building blocks. And if you really know what are the plots for all of them, or you can just use 20 log omega thing, 20 log 10 into 20 log 10 of the magnitude thing. And for phase also, if you try to draw the Bode plot, you get the plots. And just a second, I'm not able to see my screen. Yeah, if you draw the Bode plots and superimpose them, because everything is in log. If everything is in log, you can really add them up. If you can add them up, all the Bode plots can be added together, and you can get the resultant one, which is corresponding to the complete transfer function of the system. So if you draw the plot accordingly, you'll be able to see that these both points would serve as some corner frequency for the system. Okay, in this case also the same thing is happening. These both points serve as corner frequency of the system, and you'll see that this is the intermediate frequency in which the system, the frequencies are being attenuated. You have the lowest gain present over here. That means that this frequency is not being passed through the system, and you're attenuating these frequencies, and you have the other frequencies present. So these corner frequencies would really help you in getting what are the frequencies that are being attenuated, and they are the
Okay.
intermediate frequency. I
Okay,
hope it
ma'am.
is clear.
Yes, ma'am.
Okay. Okay. Then we also saw BIBO stability criteria, performance specifications for first and second order systems, where we saw rise time, maximum peak overshoot, peak time, settling time, and all of them. So we'll have some MATLAB problems also on these. We saw PID controller. It was a very basic introduction to the PID controller, and uh, you read about starting from bang bang controller, P controller, I controller, D controller, to PI, PD, PID. We went through all of these. There are problems available throughout. Root locus, it's a method. We also went through one more stability method, stability analysis method. It was Routh-Hurwitz stability criteria. The second one that we saw was this root locus. The other methods that we used for checking the stability was Bode plot, Nyquist plot. Nyquist stability criteria was the one that we covered 2 weeks ago. Then we went to the concept of relative stability, where the position of the pole really have an impact, that what is the measure or what is the margin that we have before we are reaching the verge of instability. So the gain margin and phase margin help us determine that if both of them are positive and the system is stable. Then we went through lead lag and lead lag compensator. So all of these were covered in the course. Besides these, there were some MATLAB problems that I showed as we went through the course, root locus, and all of them are really simple commands. We'll have some more MATLAB questions in the next session, but this is it for today. Thank you.